Welcome students for the chemistry lecture, and up till now in the chemical kinetics you have studied what is chemical kinetics, the rate of reaction, what is the average rate, what is the instant rate, then what is the molecularity, order of reaction, zero order reaction, first order reaction, second order reaction with examples and characteristics. So let us revise these points in short. So chemical kinetics, it is the branch of physical chemistry which deals with the study of a rate of chemical reaction and the factor affecting their rates and mechanism by which chemical reaction occur. Then the rate of reaction is defined as the change in concentration of the reactant or product per unit time, and mathematically it is given as dx by dt, where x is the decrease in concentration and t it is the time. Okay, then average rate, it is defined as the change in concentration of a reactant or a product divided by the time interval over which the change occurs, and instantaneous rate is defined as the rate of reaction at a specific instant. Then a rate law, it is defined as the experimentally determined equation that expresses the rate of chemical reaction in terms of molar concentrations of reactant. Then the next term that you have studied, that is the order of reaction. It is the sum of exponents to which the concentration term in the rate law equation are raised, or it is the number of either atoms or ions whose concentration alters or changes during the chemical reaction, and that number it is called as order of reaction. And order, it may be fractional number or integer. Okay, it may be positive or negative. Then the molecularity of a reaction, it is defined as the number of reacting species, atoms, ions or molecules involved in an elementary reaction. And remember that molecularity of the reaction may be or may not be same with the order of reaction, and molecularity, it is always integer and positive value. Then the rate constant or specific reaction rate, it is defined as the rate of reaction when concentration of the reactant is unity. Okay, then the zero order reaction is the chemical reaction in which rate of reaction is independent of concentration of reactants and remains constant throughout the course of the reaction, are called zero order reactions. Then the first order reactions are the reactions in which rate of reaction depends on concentration of only one reactant. That reactions are called as first order reactions. Then you have studied the pseudo unimolecular reactions or pseudo first order reactions. The chemical reactions that have higher order true rate law but found to behave as a first order. Okay, here the concentration of one of the reactant, it remains constant because one of the reactant, it has a greater concentration, and so it does not alters the rate of reaction. Such reactions are called as pseudo unimolecular reactions or pseudo first order reactions. Then you have studied what is the half-life period, the time required for a chemical reaction to reduce the original concentration to the reactant to half of its initial value is called as half-life period. I repeat, it is the time required for a chemical reaction to reduce the original concentration of the reactant to half of its initial value. Then the integrated rate law, that is the equation which are obtained by integrating the differential rate laws, which give a direct relationship between the concentration of the reactants and the time. That equations are called as integrated rate laws, and you have learned the integrated rate laws for the first order reaction and second order reaction with equal initial concentrations and with unequal or different initial concentrations. Here we see one by one. Here the derivation for first order reaction, and you know the first order equation, it is this. Here 2.303 divided by T into log of initial concentration A divided by the concentration at time T, and we write this as A minus X, that is the K, it is equal to 2.303 upon T into log to the base 10 A divided by A minus X. This is the integrated form of velocity constant K of the first order reaction. This is the integrated form of the first order reaction. Then you have studied the characteristics of first order reaction, that is the half-life time of the first order reaction is given by 0.693 divided by K, where K, it is the velocity constant. Then you have learned the derivation of velocity constant K for a second order reaction with equal initial concentration, and you have derived the formula. Here that formula is this one. K, it is equal to 1 upon A into T into X upon A minus X. Okay, 1 upon A into T into X upon A minus X. This is the formula. And the half-life time of the second order reaction, it is given by 1 upon A into K, and this equation signifies that for second order reaction the half-life is inversely proportional to the initial concentration. Then these are the some equations. Here we have seen this. Okay, then the second order reaction with unequal initial concentration and its formula. Here it is. Yes, here we have considered A and B, these are the products. That formula is here. is not here. Okay. So the next point, that is the examples of second order reaction. We see the examples of second order reaction. The there are number of examples of second order reaction, and for your syllabus there are few examples of second order reaction. The first example of second order reaction, that is the saponification of ethyl acetate, that is the hydrolysis of an ester in presence of alkali. The saponification, it is the process of making of soap. you know Saponification, it is the process of making of soap. In case of hydrolysis of an ester in presence of alkali, that process is known as saponification of ester. And the hydrolysis of ethyl acetate occurs as follows. The formula of ethyl acetate, it is the CH3COOC2H5. If we add NaOH to the ethyl acetate, we get sodium acetate plus here ethyl alcohol, and the velocity constant K is obtained by using the relation here K, it is equal to 1 by T into X upon A in a bracket A minus X, where X, it is the decrease in concentration, this X, it is the decrease in concentration, here A, it is the initial concentration, and the T, it is the time. Okay, then the another example of second order reaction, that is the reaction between potassium persulfate. The formula of potassium persulfate, it is the K2S2O8, and potassium iodide, that is Ki. Remember, the reaction between K2S2O8, that is the potassium persulfate, and potassium iodide, and this reaction is the second order reaction. Here persulfate and iodide, they react with each other with liberation of iodine. Okay, the reaction between potassium persulfate and potassium iodide, it takes place as follows. Here K2S2O8 plus 2Ki, they gives potassium sulfate plus iodine. Here in this reaction, iodine is liberated, and this reaction is a two-step reaction. In step first, persulfate ion, that is S2O8 minus minus, it reacts with iodide ion to form S2O8 3 minus, and this step is a rate determining step or slow step. And in a second step, the product of first step, that means S2O8I 3 minus, it reacts with another ion of iodide, that is I minus, to form sulfate ion, and I2 is liberated, and that reaction is a fast reaction here. And overall reaction is persulfate ion, that means S2O8 minus minus, it combines with two iodide ions to form sulfate ion, two sulfate ions, and iodine is liberated. And from the overall reaction, it seems that this reaction is of third order, because one persulfate ion and two iodide ions, they react. Therefore, this reaction, it may be third order, but in a practical purpose or in a practice, it is found to be this reaction is of second order. And the rate of this reaction, it is given by K into concentration of persulfate ion into concentration of iodide ion. Okay, that is the, it seems that this reaction is of third order, but in actual practice, this reaction is of second order, where the rate is given by, here rate, it is equal to K into persulfate ion concentration into iodide ion concentration. And in this case, the slow and the rate determining reaction is the reaction between persulfate ion and the iodide ion. Okay, these are the two examples of second order reaction. And the velocity constant K of the second order reaction, where initial concentrations are different, it is given by the expression K, it is equal to 2.303 divided by T in a bracket A minus B into log to the base 10 B in a bracket A minus X upon A in a bracket B minus X. Then the next point, determination of order of reaction. That means methods to determine order of reaction. There are number of methods for determining the order of reaction, and for your syllabus there are only three methods. The first method, it is the substitution into formula. That is, we have the integrated equations or integrated forms of equations for first order, second order with equal and unequal initial concentrations. And if we substitute the values of initial concentration, decrease in concentration and time, the K values are constant. You know, that method, it is the integration method or substitution into equations or integral rate expression method. We have the equations for velocity constant of various reactions as follows. You know, for first order reaction, we have K, it is equal to 2.303 upon T into log to the base 10 A divided by A minus X. And when in this equation we put the values of T, the values of A, the values of A minus X, we can find that all K values are constant. And when we use this formula, we can say that this reaction is of first order. Then, in case of second order reaction with equal initial concentrations of reactants, we have K, it is equal to 1 by T into X upon A in a bracket A minus X, and for different initial concentrations we have, this is the formula. Then by substituting these values, we can show that that reaction is either with equal initial concentration or with unequal initial concentration. That is, in this method, the amount of reactant decomposed, that is the X, at a various intervals of time t is determined experimentally. These values are substituted in various velocity constant equations of first order, second order, and the order of reaction is determined by that equations, which gives a satisfactory constant value of the velocity constant K. This method is of trial and error, but still it is extensively used. Remember that this method is of trial and error, but still it is used. Then the graphical method. Okay, to confirm whether this reaction is of first order or second method. Okay, that is the graphical method. The order of reaction may be determined by plotting different functions of concentrations against time at a different concentrations we have. Okay, for first order reaction, if we plot the graph of log of a upon a minus x versus time, or the log of a minus x versus time, a straight line is obtained, and we can say that this reaction is of first order. Then in case of second order reaction, when we plot the graph of x upon a minus x or 1 upon a minus x, the plot, it is plotted against time t, and if straight line is obtained, the reaction is of second order. Then in case of unequal initial concentrations, if we plot the graph of b in a bracket uh, log of b in a bracket a minus x upon a in a bracket b minus x, or a minus x upon b minus x versus time, if we have a straight line, we can say that this reaction is of second order. And then the last method, that is half change or half life time. And this, by using this method, we can find the order of reaction. All of you know, in case of first order reaction, the half-life time is independent on initial concentration. Here we can say that this equation, time, it is inversely proportional to initial concentration. Then in case of second order reaction, half-life time or time taken to complete any fraction of the reaction is inversely proportional to the initial concentration in case of second order reactions. Okay, and in general we can say that the time taken to complete any fraction of the reaction is proportional to the inversely proportional to the 1 upon a raised to n minus 1, where n, it is the order of reaction, and t, it is the time required to complete a certain fraction of reaction or half life time. And by using this, we can say that that method is of either first order, either second order, or either third order, depending on the equations. Okay, then the another point, that is the Arrhenius equation, we will see later on. And the effect of temperature on the rate of reaction, and it is explained with the help of Arrhenius equation. We will see later on. Thank you.